Welcome to part 2, problem definition. In this section, we're going to break down how to conceptualize and structure a hero problem. In non-hero development, problem definition typically includes two aspects: functional, what it should do, and technical, what it should be made up of, how it should be built, how it should operate, etc. A hero problem has a third defining aspect: modeling. In terms of modeling, this segment outlines ways to divide the parts of a problem to arrive at a set of distinct sub-problems that are strung together in an overall architecture or pipeline. We're going to discuss three different types of problems: data-driven problems, principle-driven problems, and problems driven by experience or knowledge. What is a data-driven problem? A problem is considered to be data-driven if data takes foremost precedence in arriving at the solution. Examples of data-driven problems include image recognition and natural language processing. A specific example is Apple's Face ID facial recognition system, which uses data points from multiple depth-sensing cameras to unlock your device. Next up are principle-driven problems. What's a principle-driven problem? A problem is principle-driven if algorithms, methods, and techniques take precedence over data and expert knowledge. For example, a financial market simulation is principle-driven because it's guided by cause and effect relationships and model principles. Generative design systems are also principle-driven. This leads us to our third type of problem: knowledge or experience-driven. So, what are knowledge-driven problems? A problem is knowledge-driven if the primary driver is formal or expert knowledge. There can be quite a variety of examples of knowledge or experience-based problems, everything from recipes that are to taste to marketing and sales problems where things are known from past experience. These require knowledge in addition to a grasp of the principles involved in order to be solved correctly. Now that we've got some of the verbiage out of the way, it's time for an example. Let's think about a model developed for autonomous driving. How would this model learn about its world? To start, a driverless car must have several sensors feeding the model data. There's cameras and radar and LiDAR and microphones, throw in computer vision, definitely some sonar and GPS, and likely a bunch of other types of sensors. But maybe we got ahead of ourselves. Every autonomous driving model must have its baseline data. What are the size, shape, weight, and dimensions of the vehicle? How many horsepower does the engine have? How do those horses affect the acceleration of the vehicle? What's the braking distance at different speeds? In all of these regards, principles of physics and dynamics come into play. What if the surface you're braking on is slick from rain? More physics and dynamics. Does the model understand the concept of rain? How does it know it's raining? Is anyone in the cabin? Do they need to see clearly? Maybe the model should turn these wipers on and defog the windshield. What speed should be used for the wipers based on the rain? What's this thing approaching? How should the car and its passengers interact with this thing approaching? Are there general rules that should be followed for interacting with other objects? But wait. Are we reinventing the wheel here? While some considerations of how the model should behave can be based on general preset rules and raw data input, in order for an autonomous vehicle to drive properly and without error, it's helpful to also have expert knowledge of what might occur in certain situations, especially when considering what a human, and often erratic, driver of another vehicle is likely to do. Let's take a sec to think about a model built for marketing analysis. Let's say that the execs at the Amazing Beverage Company want to analyze the performance of their different flavors regionally. Sure, you could just feed the model sales numbers, and that'd tell you that ABC Tahini-infused watermelon lemonade is a top seller in these regions. And it'd tell you when these beverages sold the most, how many units, the sizes that are most popular, etc. But what if you need to know why? Why does that delicious, mouth-watering ABC Tahini-infused watermelon lemonade sell so well in the summer in LA as opposed to, let's say, southwestern Kentucky? Maybe it's the demographic of the people in the area, or the foods that are complementary to the beverages, or the locations where your beverages are sold. say out of a corner store or restaurants versus out of a supermarket. Or maybe they just like their tea a little bit sweeter in Kentucky. That's where expert knowledge and experience would come into play. Models sometimes need problem analysis from the experts to make them run properly. So now you can chill a lot more ABC tahini-infused watermelon lemonade in southern Kentucky, especially if it's mixed with a little sweet tea. Want to do one more? Let's do one more. Consider an airplane wing. They're all different types, from fighter jets to passenger airliners to single-engine Cessnas. What's consistent when designing the wings of a plane is that certain designs fly and others won't. For domains like engineering design, principles form the primary input when building models. Principles include well-defined methods and procedures used to calculate cause and effect relationships. Of course, these metaphors are not limited to driverless cars, marketing, or engineering design. Did you know there are ways to model intuition? A model can infer certain relationships between things based on a little bit of experience or expert knowledge. Let's say we want a model to determine relationships between a group of people who are connected on a social networking platform. And for those of you thinking there are massive privacy concerns, let's all have a collective sigh of relief here. We'll say this model is only used to make each user's experience more intuitive and to improve the UX of the system, but it isn't available to other potentially snoopy humans or companies. Doesn't that put you at ease? Maybe not. Okay, let's get on with it. The model would have access to general data, i.e. photos of users list of friends, and a record that person X has contacted person Y. The model would easily be able to figure out who each user is connected to and who's friends with who. But here's the real question. Who is whose best friend? I mean, Bo and Katie are close, but are they close? Oh my God, are they besties? The degree of closeness would be something that the model wouldn't be able to discern by relational understanding alone. A bit of human knowledge, almost like a hint to the model in this case, is necessary to give an understanding of the degree of closeness. A human snoop, let's be honest, would know that in order to infer a degree of closeness, you should check and see if these two people are pictured together, and if they're close together in pictures, and to check not just how frequently they interact with each other, but also when they interact with each other. Here's a hint to your model. Do they hang out on the weekends? Wait, they posted a picture at the bungalow having drinks? Why wasn't I invited? But I digress. Expert knowledge and human insight into relationships between factors can help the model infer things that it would not on its own. If the model wants to determine whether these two people are related through work, the system architect may help by adding some knowledge. For example, do these people contact each other at times that people normally designate for work? So 9 a.m. to 5 p.m., Monday through Friday? Do they communicate solely via email? Are the communication channels that they use attached to company domains? Do they contact each other on weekends or after hours frequently? Are several other connections also people who work at the same company? All of these factors could help the model arrive at an understanding of what type of relationship these two have. If we're not sure, but have a good feeling about something, that can be modeled also. Fuzzy logic may be used to describe uncertainty and approximate reasoning. Let's go back to those friends who went to the bungalow without me. Hurtful. The model may gather some understanding of the relationship between Bo and Katie, but it may not be sure about the full context of their relationship. How do they know each other? Do they work together? Are they connected through a much cooler third person who is a better friend of both of them? Probably. Is there a familial relationship? The answer to all of these questions is likely maybe. The model would use probability in this case to determine a degree of uncertainty. It's 90% sure they're friends, 80% sure they're close friends, 95% sure they aren't family. You get it. Let's move on. Here's a couple of exit notes. In some cases, there may already exist models or simulations for part of the problem. The challenge is then to calibrate that model or to find the best configuration for a particular situation or use. Given the configuration, it is possible to simulate its behavior, but you still don't know which is the optimal configuration that maximizes the performance. When you're designing a model, consider if vital knowledge might be lost by resorting to a purely data-driven approach. Alternately, principles may outweigh expert knowledge or data. If so, a principle-driven approach may be well suited for you. Kato AI.